Hello everyone. So we got our LED lights blinking sequentially, and we're going to need to build two more of these same circuits for the full LED game. But before we do that, I kind of want to concentrate on this circuit and build a finite state machine for this small circuit here before we build one for our larger game. And this is because, I feel the finite state machine is an important part, and to really kind of understand the principles behind it, I think it's best to work on a simpler circuit before going to a more complex one. So right now we can control these LEDs by kind of manually plugging the control signals, whether in like high or low. And of course that's not going to cut it, and so that's why we need the finite state machine. But before we build our little mini finite state machine, I want to add two more circuits. One, it's going to be the push button from the player, and the second one is going to be a reset button, because if I pause the clock, it's going to be nice to be able to reset the LED to kind of a starting position. And so let's see how we could do that. So I got a potential circuit that could accomplish this task. Now, if you recall, there were two types of counters that we looked at. One was the 161 and the other was the 163. Now, the 161 has the advantage that the master reset is jam loaded, whereas the 163, it's a synchronous reset, and therefore it needs the clock signal. So that really means is that resetting the 161 is way simpler than the 163. If we wanted to reset the 161 chip, all we would need is our 5 volts, a resistor, and the push button. And basically, the reset pulse would come from this line right here. So normally it would be held high from our 5 volts. And if we wanted to reset, well, we just push down on our push button, it would go low, and boom, it's reset. But for the 163, it's a little more complicated, because we need to have our master reset low, and then once it's low, we need the clock pulse, kind of that upward edge of the clock. So one way we could do that is right here is to add an inverter, and therefore anytime this master reset goes low, it's going to take that low signal, I put the little bubble on this side, and produce a positive clock pulse right here, which we could send to the clock. And that looks like it's going to work, but we kind of have to be careful, because clearly before the clock pulse goes up, the reset pin needs to be low, and it has to be low for a minimal amount of time. And if you check out like the data sheet, it says that the minimum time is about 15 nanoseconds. So it's incredibly short time, but you still got to satisfy that it's called the setup time. You got to satisfy that setup time. Otherwise, your counter can get unstable and start oscillating back and forth and kind of have that metastable state, which we talked about earlier with a slow rising clock pulse. And I also checked the data sheet for these kind of inverters. I had some Schmidt inverters, and they said that the delay going through one of these gates is about 20 nanoseconds. So you figure that should be good enough. 20 nanoseconds is longer than the 15, and so we should meet the setup time. However, the margin is only about 5 nanoseconds, which is a very short amount of time, to say the least, especially kind of on our breadboard circuits right here, where we're just hooking things up with wires, instead of like a precise PCB board. So this might work, but then it might not, and I don't know, it's a little close. A second possibility is this circuit over here. You can see it's the same setup, but in between the push button and the inverter, I place a little low pass filter. And so I have the timing diagram right down here. So once we hit the push button, the master reset goes low. Right here at node A, it's going to follow that master reset pin and slowly go down, because the capacitor is going to be discharging, right? When this guy is open, the capacitor will be charged up to 5 volts, and then when he's pushed down, he's going to discharge through that 100K resistor to ground, and so we'll get a nice slow drop in our voltage. And as it's dropping, we stick a little Schmidt trigger here, and basically once it reaches a certain threshold, well, the output is going to snap right up to high, and then we'll get our clock pulse. And the timing from kind of this negative going edge on the master reset to the clock pulse is going to be dictated by the time constant of this capacitor and resistor, which is about 1 millisecond. And so we might get, on the order of 1 millisecond. It kind of depends on the hysteresis of this of our Schmidt trigger. And if you want to learn about hysteresis, the EEV blog dude Dave, the YouTube guy, he's got a cool episode just on that explains the usefulness of that circuit, and it's worth checking out. And no doubt there's probably tons of other videos on this. It's a very common thing, this little symbol here you'll see. Okay, but this is kind of generally the function, and so let's check it out. Oh wait, hold on, no. So this will create our clock pulse, but we have to remember that the clock pin is also going to be fed by our actual clock circuit with a 555 timer, and you just can't put different inputs on the same pin, because one might be high, one might be low at the same time, and that's not going to be good news. So I've redrawn our reset circuit here, and this part goes to our master reset pin, and right here this is going to need to go to our clock pin. But of course our actual clock circuit is going to have to be connected to the clock pin as well, and so this is why I included an OR gate. So basically when the clock is running, well, this reset should not be running, and so the clock is going to go through, and when we want to reset it, our circuit, well, the clock shouldn't be running, and then the reset will go through. And so apart from the resistor and capacitor, we're going to need a Schmidt trigger NOT gate and an OR gate. Now, instead of using kind of 2 different chips just for 1 gate each, I can save a bit of space on the breadboard by using a 74 HCT 132 chip. And basically it's just a NAND gate with that Schmidt trigger type of functionality. And so essentially these NAND gates can be used to kind of make any sort of logic, because if you want a NOT gate, well, then all you got to do is tie the 2 inputs together of your NAND gate, and then now it becomes a NOT gate. And also there's this kind of cool little identity where if you have an OR gate, that could become an AND gate, and all you have to do is negate the inputs and the outputs. And it also works vice versa. An AND gate can become an OR gate by just negating both the inputs and outputs, kind of like De Morgan's theorem is what it's called. And so if we just take these 2 identities, well, this here a NOT gate, we basically I've redrawn it here, a NOT gate and an OR gate. Well, this one can just be a NAND, and this OR gate can be this sort of NAND with these 2 NOT inputs. And so these 2 NOT inputs can be created with 2 NAND gates themselves right here. And if you look on this line right here, well, you have a NOT gate and a NOT gate, and then it goes into your NAND gate here. But 2 NOTs in a row, I mean, they're just canceling each other out. And so at the end, you just need 2 NAND gates. Here for the clock, our normal clock is going to come in and and get knotted with this NAND gate here, and finish it off with another NAND gate, and that should do the trick. And basically, we just need one chip instead of two. So let's check it out on the breadboard here. And I've kind of pushed the clock circuit on the side here to make space for our reset circuit. And so this is our the Schmidt-Trigger NAND chip, and I'm just using the two gates below, and so the gates on the top here I've all tied to the 5-volt rail, and kind of that's just how we should normally do our chips when you know, when we have unused gates. So we can just power this up, and if we let the clock run for a little bit and then just pause them, and then our reset should work. And also if we move through, and then the reset should work too. And if we look at our scope right here, we can see how the reset looks. Zoom right in. And perhaps I should zoom in. And so our yellow trace, that's what's going to go to the master reset. It's hard to see, but here it kind of is. So once that drops low, well, the little node A we called it on the capacitor, well, that's going to slowly discharge. And let me just put them back down so you can see how it goes. And once it discharges to about a volt right here, then our clock suddenly strikes high. And by that time, there's about, it says here, about 1.7 milliseconds or so. So we're gonna have our master reset at low for about 1.7 milliseconds, and then our clock circuit comes up and resets our circuit. Also note how the output of our clock now goes straight up to 5 volts and is no longer stuck around 3.5 as it was with the output of our BJT 555 timer. And this is thanks to our NAND gates with their CMOS outputs that are able to pull the voltage straight up to the positive rail. So it's just a little bonus that we've added to our circuit. Okay everyone, thanks for watching the video. Bye bye.